Since we're sticking to the very end, so the last talk of the workshop is by Oliver Hammerling, who is at the University of Warwick.
Great, thank you. Thank you for the organisers. And I'm aware that I am standing between you and going home, so I'm going to try and keep it quick. And also, my meme game is very low, so I'm just going to put a picture of my dog. That's the only meme of the thing. He's kind of the equivalent to Tim Swearjar. Every time I get frustrated with GPs, I go and give him some love. And needless to say, he's a very loved dog. Hang on, let me find my slides again. Okay, yeah, so I'm here to talk a bit about kind of using GPs and modeling air quality in London. So this is part of a big project at the Turing. I'm trying to model and predict air pollution in London. I'm just going to talk about a very small part of my research, which is part of this project, and it's kind of part of the theme that we've seen a lot, which is on kind of speeding up GPs, computationally speeding up GPs. But before I get into kind of my research, I just kind of want to motivate the bigger project and why air pollution is interesting and why maybe it's a bit difficult to deal with. So this is a picture of London in 2017. What you're seeing there is kind of smog or some kind of bad air pollution. This is not stuff that you want to be breathing in, essentially. And this is something that's well known. Air pollution is kind of a major killer. This is kind of the statistic that's thrown around a lot, that every year there's 40,000 early deaths due to air pollution. And this is not just a problem in London, this is a problem all over the world. Lots of people are living in urban areas, and it's kind of estimated that 80% of those are living in areas where air quality exceeds kind of the safe limits as set by the World Health Organization. Okay, so where do we come in? Where do GPs come in? So the current models in London are these big mechanistic models. They're very expensive to run, and they can only run them once every 3 years, so it's using out-of-date information, and it only gives annual averages. So this really limits what people that want to do kind of real-time policies, kind of limits what they can do. So they need more kind of data-driven models to have more real-time information, I suppose. So that's where the London Air Quality kind of fits in. The London Air Quality Project kind of fits in. And just to kind of summarize the aims of the project, we want to bring information from a bunch of different data sources, bring them into a single place for analysis. There's a bunch of different sensors. In London, there's actually quite a lot of sensors compared to lots of cities in the UK. There's around 70 high-quality ones, but there's a lot of different ones, lots of cheap ones, and we want to bring them all into one place and start constructing models. What I'm going to be talking about today is spatio-temporal models. So we're going to be constructing spatio-temporal forecasts and estimates of air pollution across London. And then some people who are smarter than I will use these to do some cool stuff with it, like constructing low pollution running routes across London. So this is kind of why GPs come into this, because we need uncertainty. We can't just provide a forecast and be like, this is what it's going to be. People need to know when a model knows what it doesn't know, and people need to have that uncertainty so that they can actually do informed decision-making on top of these things. Okay, so just to give you some idea of what air pollution data kind of looks like, this is I don't remember what site this is, but this is a couple months worth, a year's worth of data, maybe, from a single site in London. So air pollution is an umbrella term, so there's actually different pollutants. You can have NO2, PM10, or some kind of oxides, particulate matter, which is basically dust. And there's lots of structure in the data. So this is kind of where there's lots of things you can do with this. You can do multitask models. You can try to learn the correlation between these things. What we're going to be focused on today is how do we handle the fact that we have loads of data. So this is the data set that we are going to be focusing on. This is from the London Air Quality Networks. This is run by King's College, I believe. It switched to Imperial for a bit, but I think it's back at King's. And there's around 100 sensors in fixed sensors in London, and they record air pollution every hour. So once you start to look at this over like a yearly scale, you quickly get to the amount data sizes that GPs just can't run on. So that's where we're going to be talking a lot about computationally efficient GPs. So 6 months worth of data is around 400,000 observations. On my laptop, I can run with 2,000 observations using naive GPs, so you can kind of see where some of the problems might be coming in. There's lots of temporal structure. Why is this going to be a problem? Well, kind of the standard methods might be to try and apply a sparse GP here, but then you're going to need lots of inducing points, and then you're just going to smooth over all of this structure. So there's some of the challenges we're going to be seeing in a second. And of course, the data is never perfect. Evolution is meant to be positive, but we have negative values, and we have lots of missing observations. I'm actually not going to talk at all about that, but it's just some interesting challenges if you deal with this data. Okay. So now I kind of get to my research, essentially. So this is from a paper, I actually titled this, Spatio-Temporal Variational Gaussian Processes. This is work that I did with some great people in Finland, so Will Wilkinson, Arno Solin, and Theodor Milas, and Nikki Loppi. And just to kind of give a very high-level overview of what I'm going to be talking about. Hopefully, some of these terms are now kind of familiar, based on all the stuff you've been seeing at the summer school. So what we want to do is we want to build kind of a GP model to model the spatio-temporal phenomena. So we want to be modeling air pollution across London and across space and time. And as we know, the computational burden of GPs makes this difficult. But we've already seen quite a few, or two main methods to handle this. So that's sparse Gaussian processes and also state-space GPs. We saw that today with Tim's talk. And these are good, these are great. But sparse GPs, they will start to oversmooth once you have lots of structure in time. So you're going to need lots of inducing points to compensate, but then you suddenly hit computational problems because of the fact you have loads of inducing points. And state-space GPs, these are brilliant, they're linear in time. But once you have lots of spatial points, you suddenly hit computational limits there as well. And I'll get into that later. So what we're going to try and do is to kind of combine them together and try to get the best of both worlds. And I'll try to convince you of that. Okay, so this is the too long didn't read / wanted to get my train. And if you know this field, then you can probably walk out after this. So the way we're going to do this is by proposing an SVGP, a sparse variational GP. We're going to represent our proximal posterior as a state space model. And then we're going to show that we can compute the full elbow using Kalman filtering and smoothing. And this model is going to be equivalent to an SVGP, but because we're using Kalman filtering and smoothing algorithms, it's going to be computed at a fraction of the cost. Don't worry if that didn't make some sense. That's just for people who kind of are in the field. Okay, yeah, so this is the rest of the talk. I'm going to flash up some pictures on GPs. I think we've all heard the definition of GP to death now. And then I'm going to also do the same with fast GP. I believe you've all had some great introductions to that. And then I'm going to slow down a bit when we get to state-space GPs. I'm going to focus on how to construct a spatio-temporal state-space GP. And then I'm going to slow down even more when I start talking about natural gradients, because we're going to be working within this framework that allows us to combine variational models and state-space models. And then hopefully the rest will be easygoing. Okay. So a GP, we have some data, we fit some nice functions, we have some nice, well, there's no samples here, but we can make some nice samples. So GPs are nice, and we get uncertainty, which is very nice. I think we all know all this by now. I'm going to use X and Y for my input-output data. I'm going to have n observations, just for notation. And the key point is that they are kind of slow. So inference and training has this n-cubed computational complexity. But that should all be familiar by now. Okay, so quick recap on sparse GPs. So the main idea with a sparse GP is that you probably don't need all of these great observations to fit a good model to this data, to this data set. What happens if we just had a reduced set of observations? I don't want to just take them from the data, because I don't want to throw things away. So I want to somehow learn some pseudo-observations or some inducing points to kind of
compress the data set that is there. So what about if I did something like this, where I had these black pseudo-observations, which don't exist exactly in my training set, but they live in the same space. And then if I place a GP on that, I get something that looks quite close to my original full GP, but at a less computational cost. So that's kind of the motivation of sparse GPs. There's also maths here, which I believe you should have all seen already. But just to I just want to highlight a few things about this. So we're going to have M inducing points, and the idea is that you have M much smaller than N. That's kind of where the computational benefit comes in, when you have much less inducing points than your data. And then there's some computational tricks to define your posterior and posterior, such that things cancel, and such that you get nice computational costs. I'm just going to stop. Is this all not new? This is all known by now? Or do I need to go back and recap, or is everyone okay for me to kind of accept that variation with sparse GPs are okay? I see nods. I'm going to take that as a good thing. Okay, so SVGPs are great. They're very flexible. They're very applicable. You can apply them to lots of different models. But the problem with SVGPs is when you want to start to model data with lots of structure. And this happens a lot when you're modeling time series. So this is just like a schematic picture, just like a toy data set. So on the left, I have this picture, which is basically just saying we have low number of reducing points. This is meant to be in space and time, and I'm just plotting a time series. And the idea is that if I have a low number of inducing points, the model fit that I'm going to get at the end is basically just going to over-smooth through all of my data. Why does this happen? Well, there's just not enough. I just can't capture enough information within my inducing points because there's so few of them. Now, this is not rubbish, as in my inserting looks good. It's just sometimes you want to capture the structure in the data. And when you want to capture the structure in the data, you're then thinking, oh, I need more inducing points. And then suddenly you're hitting M, getting close to N, and things are computationally intractable again. So yeah, if you want to have lots of inducing points, you can now capture all this interesting structure, but it comes at a computational cost. Okay, so I said at the start there was kind of two popular ways of kind of speeding up GPs. The first one is sparse GPs. The second one is state-space GPs. We already had a great talk by Tim today on state-space GPs. He was focusing on the time series setting. I'm going to kind of quickly recap that and then show how you can easily extend that to the spatio-temporal setting. And then we'll discuss some of the limitations of this as well. So as Tim already said really well, state-space forms of GPs kind of exploit this dual parameterization of GPs, where they are the solution to linear time invariant stochastic differential equations. The kind of intuition is that like an ODE is describing how a function evolves over time, but we're injecting some kind of noise through this kind of Brownian noise. And so we're describing how a stochastic function varies over time. And then if you kind of ignore some of the maths, we're just going to say this is Gaussian, my initial point is Gaussian. So the process that I'm describing is a Gaussian process. And the way you do that is you kind of construct this state, this F bar, which is going to collect the derivatives, all the derivatives that you need. And then you have these transition matrices and all these matrices that you need to do to construct your model. But this is essentially describing a Gaussian process. This is the continuous form. And as Tim already said, we can discretize for free, as in, because this is a linear time invariant system, we can discretize without error. So when I have data, I can now construct a finite discrete state space model, which I can now use Kalman filtering and smoothing to compute. So in this work, all I care about is recovering GPs with given kernels. So all I care about is constructing a GP with a Matern kernel. And all you have to do to be able to do that is to go to the book by Arno Solin and Simasaka, look at the Matern kernel page, and they will give you the form of these A's and Q's and H's and the initial conditions, such that you are recovering a GP with a Matern kernel. And now I've just copied and pasted it here, just so we can see what it looks like. So this is a Matern 3-2 covariance kernel. If I want to construct a GP as a state space form with this, I would just construct my A with this form, my L, and my P infinity, or my kind of initial state with this form. This is all once you get to this stage, it's all okay. So you can just go to the book, get to the reference, and steal it from there. And this is just like a little example just to show how this would kind of work as an algorithm. So you, as we said a few times, you run a Kalman filter and smoother. So in this first step, we have some data which is denoted by these kind of these crosses. We're going to run our forward filter. So we're going to do one pass through the data going forward in time. We're going to collect a bunch of stuff. And then we're going to run the Kalman smoother, or the RTS smoother, going backwards in time. And we're going to compute a bunch of quantities that corresponds exactly with the posterior distribution, as if I'd run the GP in the normal case, or the batch case. So if you just use your standard GP equations, you would get this guy. But it would cost you n cubed computation to do it. If you ran a Kalman filter and smoother, you would first filter, then smooth, and your marginal variances would coincide exactly. So this is an exact algorithm in the linear case. Cool, so this is just the temporal setting. But we can extend that, and well, people have extended this to the spatio-temporal setting. And the way it works is that there's a couple assumptions that you need to make. You need your data to lie on a spatio-temporal grid. You need your kernel to be separable between space and time. So you have one kernel, Matern, on time, and you have something on latitude and something on longitude. You take the product of them. This is a separable kernel. And then you can immediately write your GP as a state space with this representation. Now, what does this mean? Well, you take your new state is essentially going to stack. Sorry, let me rewind. So you have NS spatial points. Imagine you're going to define a state space GP individually on each of those spatial locations. You're going to construct a state that kind of concatenates all these individual state space GPs together. And then the correlation between them is going to get injected into the noise. So your new state is just basically going to be NS stacked states from each of your spatial points. And each one of these is going to be however many derivatives that you need. The great thing about this is that nothing's kind of changed. We've constructed a fun state. We've constructed a nice way of making our kind of transition matrices and everything. But we're still just in a state space form where we can run a Kalman filter and smoother. It's still linear in the number of time points, but now we are cubic in the size of the state. Well, we're always cubic inside the state, but now our state depends on the number of the spatial points and the number of derivatives we need. Yeah, and this is just saying that, again, this is all exact. If you had a GP with a separable kernel on time and space, you're computing the same posteriors. It's just another way of computing them. So just to kind of be a bit more clear, I have an example kind of showing this. So here we have a bunch of points on a grid. So time is on the x-axis and space is on the y-axis. And now we're going to filter through time. So this is what this first panel is showing here. This is the example of pausing the filtering halfway. We're going to filter through time. And as you can see, as I'm filtering through time, I'm kind of constructing my spatial slices as I'm going along. And then when I smooth, we're going to smooth over in time again, and we're going to recover the posterior distribution or predicted posterior distribution, which will coincide exactly with our batch case. Okay, maybe I paused there just to ask if anyone is lost or confused or if it all makes sense. Yes?
What does filtering, what does that filter do exactly? Like you have the time series, and then...
Yes. So your filter is coming from computing this discrete state space. So you take you have a bunch of time series at spatial locations. And so we're going to construct a state such that for each spatial point, I'm going to concatenate them all together. So I'm going to have at f0, I'm going to have ns kind of independent f-bars here. And then I'm just going to construct all these kind of matrices based on these Kronecker things. But you notice here in the noise, I get my ks here. So this is the correlation between space. So as I'm kind of filtering, they're not independent anymore. The correlation between space is kind of captured in that noise term. So the way you run it is you essentially concatenate, you create the state, which is basically stacked across all of your spatial points, and then you have a finite dimensional Kalman filter again, and then you can just run the filter and smoother. What I'm plotting here is actually the predictive distribution coming off this. So you can compute your GP conditionals, your predictive distributions on top of this, and that's easy to do. But yeah, I agree that this maybe is, if I was just running the filter, you would only have values at where your data is. But I'm just showing the predictive here, just because it's easier to plot. Hopefully that answers your question. Yes?
To get the spatio-temporal GP representation, we need regular time observation?
Good question. So no, you don't need it to be regular in time. So basically, I'm missing some indexes here, but basically, when you compute these, some of these matrices depends on like the time difference as you're going along. What you need is you need your spatial locations to not change. And the reason you need it not to change is because you need this kind of Kronecker structure between your space and time. And if that was, at one time step, you had like 10 spatial points here, and the next one you had 10 here, you wouldn't have Kronecker structure anymore. So you wouldn't be able to write it in this form. So the time steps, they can be whatever you want, but you just need to have the same spatial locations. So that's kind of what I mean when I say spatio-temporal grid. Great. Hopefully that helps.
Does this also address only linear cases, or does it address, there is a temporal part and there is a spatial part. So it's not linear time invariant anymore, but is it still linear?
So in this case, it is still linear time invariant because everything I'm using is a, what's the phrase? Stationary kernel. Everything is a stationary kernel. But yeah, exactly. I don't know if that answers your question though.
But if there is a temporal part, then can you give an example of any specific model on which you would try this?
But if you look at the temporal part, so this would be for the single time series setting. So this is just a temporal model. Your parameters of your SDE here are just your A's, your L's, and your initial conditions. None of these kind of depend on time. These are constant as you're filtering. I actually don't know of any kernels that would be not time invariant. Because all the stuff that I do in this work would be kind of stationary kernels, where that's kind of what this is applying here, that they're not varying over time. Does that answer your question?
Yeah.
Okay. Okay. I think everyone else is happy.
So I think that the computational complexity
Mm-hmm.
in this case is still linear with time.
Yes.
Cubic with space.
Exactly.
The problem is that if you were to do GPs,
Yes.
it would be cubic in both time and space.
Yes, exactly. So you would have something like nt times ns all cubed. But this cubic term here is also a problem, which is what we're going to kind of address for the rest of the talk. So even once you get to a state size of around 50, at least for my stuff, you suddenly start to slow down a lot because of memory problems. Because if you think of it in memory, you've got lots of time points, let's say like hundreds of thousands, but then for each of them, you're having to construct this state, which is going to be 50. That's a lot of data to keep track of. And then you're doing autograd on top of this, like suddenly things get very hairy. And that's what we're trying to address through the rest of this talk. And actually, I think that's what the next slide shows. Yes? So this is what I was just saying. The runtime is linear with respect to time, but you're still cubic with respect to the number of spatial points and the state dimension. So this kind of limits the number of spatial points you can use, but also the kind of kernels you can use. Because you could use, there's representations of like periodic kernels, which need like 10 derivatives or something, but then you can't have that many spatial points. So there's a trade-off here between how many derivatives you need, so how smooth your kernel needs to be, and the number of spatial points you have. And also the trade-offs with the time dimension as well. Yes, this is where kind of the work is going to come in, because essentially what we are going to do going forward is we're going to construct a sparse GP, because we like sparse GPs. We're going to put the inducing points on a grid, on a spatio-temporal grid, and then we're going to use some magic of natural gradients to compute our proximal posteriors using state space models. And then because we now have inducing points on a grid, which is going to dictate my state size, I can basically put less inducing points in space if I need to reduce my state size. Okay, so we're now going to be talking about natural gradients. I kind of hinted at them just now. And the reason we're going to use natural gradients is because it allows us to use state space models to compute this elbow here. But just to kind of recap quickly what we're doing with the sparse, like with the variational approximation. We introduce some approximate posterior, which is going to be denoted as Q of U. We're going to parameterize it as a Gaussian, and it's going to have some parameters, which is M and S. S is typically parameterized by its Cholesky, and we're going to learn these parameters. We're going to derive our elbow, which looks like equation 15, and then we're just going to maximize our elbow. We're going to find our M and S by maximizing our elbow. So we're going to just basically do gradient descent to find M and S, or we're going to run Adam or some other thing. Okay, there's a couple of problems with this. This kind of depends on the parameterization that you use for Q of U. What about if I didn't want to parameterize my Q of U by just the mean and covariance? What about if I want to do something else? The way that would change my optimization routine. But also there's no way of exploiting or injecting kind of these state space models, which is what we want to do. So this is where natural gradients come in. Now it's quite late in the day, so I'm just going to kind of rush through these and hopefully just give you the intuition. So don't focus too much on the equations. But what we are going to do is we're going to exploit some properties of natural parameters. So I said there's different parameterizations you can use. You can use moment parameters, so you have the mean and the variance, or you can use these natural parameters, or you can use these expectation parameters. Just accept that. That doesn't matter so far. I'll kind of bring up the properties that we need as we're talking about it. And we're going to use something that's called a natural gradient. So the natural gradient is a direction of steepest descent with respect to this KLD metric. I'm just putting quotations because the KLD is not symmetric, but it's late in the day, so it is now. And the benefit of the natural gradient here is that your metric is between two posteriors now. It's not on the parameters of the posterior, it's on the actual distributions that you have here. So the idea here is that because it depends on the KLD, it's kind of invariant to the parameterization you use. I think there's a few kind of niggly bits in there that depends on your step size, but we won't get into that now. And I'm actually not going to use any of that stuff. I'm going to use a nice property of natural gradients in the next slide. So this looks pretty messy. It looks pretty hard to do. But we're working with Gaussians. Our proximal posterior is Gaussian. And there's some great things about Gaussians. And that basically means, OK, my natural gradient update is equivalent to updating my natural parameters. If I'm updating my natural parameters, if I had the standard gradient, my gradient descent would look like this. But if I'm using the natural gradient, instead of taking my derivative with respect to lambda, I'm going to take it with respect to these expectation parameters. It doesn't actually matter what I said there. All that matters is that it's very easy to compute a natural gradient. OK, cool. So we've heard something about optimizing and reparameterizing stuff and things going better. But let's dig a little bit more. So as I said, the natural gradient update is equivalent to taking, I have to take gradients with respect to my expectation parameters. Okay, that sounds cool. If I expand out my elbow, because I know what my elbow looks like, it has two terms. The first term is the spectral log likelihood term. The second term is this KLD term. I'm going to expand that out. Okay, sounds cool. So then we get this. Then what we're going to do is we're going to simplify. So I can't simplify this bit. Not really, because this is hard. My spectral log likelihood is hard. But my KLD term, because everything is Gaussian and everything is nice, simplifies to be the natural parameters of my model. Okay. I'll explain that again in the next slide. But let me just kind of say my piece here. There's a really nice property of natural parameters, which is kind of the key to all of this work. When you do a Bayesian update, so from a model, from a prior to a likelihood, you compute a posterior. When your model is conjugate, if you take the natural parameters of your prior and the natural parameters of your likelihood and add them together, you get the natural parameters of your posterior. So for conjugate models, your natural parameters are additive. We're talking about Gaussians here, so this all holds. So if we kind of remember what I just said there, I've got some natural parameters coming from some model, from something. I've got some other parameters here, which we're just going to say are natural parameters. This is now a Bayesian update from some prior to some with some likelihood to some posterior. Okay, I'm now going to switch to kind of more normal notation, or to more familiar notation, hopefully. So what did I just say there? Well, I said, okay, after a natural gradient update, I can write down my approximate posterior as a conjugate model with my model prior, this is P of U in this case, and some approximate likelihood, whose parameters are going to depend on this kind of term here. So why is this cool? Well, this looks like all of the stuff we've been doing this whole week. This is just a GP prior, I have some likelihood, I have some marginal likelihood, and I have my posterior. Everything is Gaussian, and so I can just use my standard Gaussian equations to compute all of this. Okay, I'm going to pause there and maybe just ask if I've lost everyone or if everyone's kind of following and it's okay. I'm going to repeat this about 10 times, so if you don't get it now, maybe you'll get it by the end of the talk. And I appreciate that it's late. Okay, people are nodding, so I think we're okay.
So, do you need to do natural gradients, or you could have done this without natural gradients?
So my understanding is you need the natural gradient framework such that you can write your approximate posterior kind of like this.
No, what I'm saying in the bigger picture of your purpose of combining the state space with the GP, the small GP, do you really need to do it using natural gradients, like combine them, or could it just, you could have just plain variation and inference?
Okay. So you can derive a kind of state space GP with inducing points following like the FITSI procedure. So this was done by uni, I think, 10 years ago, I don't know. But the problem is we want to use variational sparse GPs because they have better properties and it's kind of the state of the art. So the problem is when you do your gradient update using just gradient descent, if I just said, okay, I'm going to just assume my approximate posterior has a state space form, I'm just going to initialize it such that I can compute it with a state space form. When you do your standard gradient update, you're no longer guaranteed that that will be the case. Maybe you can do some line search and hack it to work or do something, but it doesn't kind of fall out that after your gradient update that your approximate posterior will have the same form. Whereas with natural gradients, that comes out very naturally. If I initialize it such that I can use a state space model, then after a natural gradient update, I'm guaranteed that I have the same form. So I can still use my state space model to compute it. Whether or not there's kind of other things you can do, I don't know. And actually, there's a lot of great work from like MT Khan's group on like the Bayesian learning rule like trying to derive a bunch of different algorithms throughout as kind of falling out from this natural gradient update. So maybe there's connections there, and you can kind of work backwards. But yeah, I'm not sure. Hopefully that answered your question.
Sorry. Kind of related to this, does this property of updating with the natural gradients apply also to other stochastic gradient updates? So like, I don't know, algorithms like Adam, something like that, or only to vanilla gradient descent?
I'm going to say I'm not sure. So there's a bunch of stuff. If you look at like MT Khan's group, like if you look from the Bayesian learning rules stuff, they've got a bunch of work on trying to show that if you start from like a natural gradient framework, like a lot of algorithms like Adam can be seen as like approximations to this. But I don't know that if you wanted to use Adam here, if you could kind of use the same things. We kind of rely entirely on the fact that the natural gradient looks like this form. And, sorry, not this form, sorry, this form. And the reason for that is because once I get to this equation, this term here, this KLD with respect to this expectation parameter, is equivalent to the natural parameters of my prior. Like, that property is the reason that we can do all the things that we're doing. So you would have to kind of see, like, if you wanted to use Adam, if that kind of property is there, or if you can kind of squidge it into that. So I don't know exactly, but yeah, that would be interesting to look into, I think. Yes, so this is just kind of a summary slide. So the natural gradient, as I kind of said, and we've had from the discussions here, kind of preserves this conjugacy. So if I initialize my natural parameters such that it can be computed as a state space model, after taking a natural gradient, I can still compute it as a state space model. The kind of really important bit is that the approximate likelihood is only updated with this guy. Because this is coming from your model prior, this is from your prior, this is your initialization. So when you're doing your update, all you're doing is taking gradients and spectral likelihood and then adding that in. And then kind of writing it in kind of more standard form, more familiar form. What does this mean? It means that after a natural gradient update, I can rewrite, or I can apply Bayes' rule now to my approximate posterior, and it has my model prior and some likelihood. The forms of these are to be determined as of yet, and that's what kind of the rest of the talk will be about. But yeah, hopefully that makes some sense. Okay, so now we get to the kind of the meat of the paper and the meat of the talk, I suppose. I'm going to show how we can use spatio-temporal state space GPs to essentially compute our approximate posterior. So just a quick game plan. We're going to define our inducing points on a spatio-temporal grid. And the whole reason we're doing that is such that this term here is block diagonal. This means that now the natural gradient approximate likelihood is block diagonal. So my Q of U now decomposes as some likelihood that decomposes over time and my model prior. And now this is exactly the form that I need to be able to run a spatial temporal state space GP. And then once I can do this, I can just plug it back into the elbow, run my Kalman filter and smoother, and compute all the terms of the elbow as kind of byproducts. So yeah, this should be easy enough, hopefully. Okay, so kind of the key thing to get this to work is something that we kind of denote as spatial sparsity. So we're going to define our inducing points to lie on a spatio-temporal grid. So this is the same as what I meant earlier by our data is on a spatio-temporal grid. The key is that it's going to lie at the same time points as our data. And the reason for that is such that all the kernels that you could need when you're running this or defining your elbow, all the kernels you need will have Kronecker structure. It means that everything I need has Kronecker structure. And as you can kind of see here, if I look at my kernel between kind of my data and my inducing points, my my inducing point locations only come into the spatial, only comes into the spatial kernels. And it's the same when I look at my KZZ. Because it's at the same time points, the only bit that's actually affected by my inducing point locations is the spatial kernel. This is one of the slides again where it's quite late, so I'm just going to kind of talk and kind of give the intuition, and I'm not going to go too much into the equations. In fact, maybe I'll just skip the slide and I will refer back to it. Yes, so this is the natural gradient update. This should be becoming a bit familiar now. We have our model prior, we have some approximate likelihood, and our approximate likelihood is updated by this partial derivative. Our expected log likelihood decomposes over time because we have conditionally IID data. But because I have spatial inducing points, when I'm computing this Q of Fn, I only need to worry about the inducing points at the same time point. So that means that only those gradients of mu kind of propagate through here, which then means that under some permutations, this whole matrix here is block diagonal, and there's going to be one block per time point. Why is that useful? Well, it means that when I switch back to the kind of more standard notation, it means that I can write my approximate likelihood, which is this guy, as being conditionally IID, but across my time points. So it decomposes over time. This is exactly the form that we need to run a state space GP, a spatio-temporal state space GP, by placing a separable kernel in space and time here, as we did at the start. So now this is just a standard GP update. Now you don't actually have to use a spatio-temporal state space GP here. You could do whatever GP you want here. You could do a batch GP, but we care about the computational, alleviating the computational burden of these GPs models. So we're going to use a state space GP. But this is just a vanilla state space GP. We're not innovating on the state space GP side. It's just a vanilla state space GP. Yes, so this is our approximate posterior. This thing is block diagonal. Now it decomposes over time. But what you can do is you can just plug your approximate posterior back into your elbow. And what you see is that all the annoying terms kind of cancel. So you get your standard cancelling due to the fact that you're using sparse GPs. But also your KLD term now cancels away, because if you remember before we had expected log likelihood minus some KLD term. Now all we have is basically 3 expectations that we have to compute. This first one just requires the marginals of Q of F, which we can compute very easily using the predictive distribution of a Kalman filter and smoother. This one just requires Q of U, which we can compute very quickly. And this one is actually the marginal likelihood of Q of U. I've just written like this to make it kind of flow, I guess. But this is just your marginal likelihood, which is a byproduct of running the Kalman filter. So all of these terms you get very easily by just running a Kalman filter and smoother based on this model.
If you go to previous equation with the expression for b tilde plus k in the lower bound.
Sorry?
It's okay. I can ask you later.
Are you sure?
Yeah, I mean, like, because I can see the term in the denominator for the bound of y tilde b tilde u. I'm not seeing the term for the marginal.
Yeah, so the marginal is this guy here. Yeah, sorry, that's actually quite confusing that I've changed notation here. So this guy here is your marginal likelihood, which is, if you guys recall, you basically integrate out u from the guy on the top of the fraction here. So that's why I've kind of written it as here, just to kind of be explicit that that's coming from the marginal likelihood. Yeah, I agree, that's a bit confusing. But then that term kind of corresponds to this term here, because this integral is now, I just write it as expectation. So I've changed notation like 3 times, so that makes sense. I kind of butchered that a bit. But yeah, hopefully that answers your question. So yeah, just like a very quick summary of the method. We're going to rewrite our approximate posterior as a solution to a linear time variant SDE. We can now compute Q of U and predictive distributions of Q of U and our marginal likelihoods very easily using Kalman filtering smoothing. We're now going to be linear with respect to number of time points, but cubic with respect to a number of spatial inducing points. So this is where we're kind of removing that dependence on NS, we're now MS. So we can now control how big our state is. We can compute the full elbow very easily. We're still linear in N because of the expected log likelihood term, but that's still linear with respect to time, so everything is okay. And the point that I just want to kind of reiterate here that might have got lost through this talk is that this is just an SVGP. Right? This is just an SVGP with structured inducing points within a natural gradient framework. It's just that we now have a way of computing it in a computational time that's linear with respect to time. So this is not an approximate SVGP method, this is just an SVGP under natural gradients. Okay, so now we get to the experiments. I'm going to pause here again just to kind of see if there's any questions. But I think we're okay. So how long do we have? Okay, we have 10 minutes. Okay, so I'm going to skip this experiment. This experiment is just trying to prove to you that, or convince you that if you had an SVGP and a spatio-temporal SVGP, they are the same model. But I'm just going to skip through and get to the kind of air pollution experiment. So in this experiment, we have 4 months worth of PM10 data in London. This is a spatio-temporal problem, but I'm just plotting like a single time series here just to make life a lot easier when we're plotting. So we're running 2 models here. We're running in green, we're running the model that I've just been talking about, so the spatio-temporal SVGP. So this is using Kalman filtering smoothing to compute the whole elbow. And below, we have the SVGP, which had the same wall time, roughly the same wall time. So with our model, we're able to use around 60,000 inducing points. And this has the same computational cost of an SVGP with around 2,000. Why is that important? Well, if you look at this blue line, the SVGP is essentially just smoothing out throughout all of this data. I'm not saying this is a bad thing. This is kind of from the assumption of the model. But if you wanted to capture this data, you would need way more inducing points. And our method is able to use 60,000, most of them in time. So we're able to start to capture a lot more of the structure of the data. That's why we're not just smoothing out throughout this whole time series. Oh, sorry, yeah.
So this is one spatial point.
Yeah, this is just one spatial point.
So do you, or maybe you have tried this, but you could just assume that all the spatial points are independent and run individual time GPs
Yes.
for each, or as you're doing here, just account for the correlations in space as well.
Yes, yes.
I guess you gain more when you do that.
Yes, so we actually didn't compare against that as a baseline, mainly because the kind of overarching aim of this model is to be fit into the kind of the London Air Quality Project, where we want to be able to predict at any spatial location in London. So if you assumed independence, you'd have to figure out a way to kind of then predict in space, which is maybe not so easy to do. Whereas if you had this full spatio-temporal model, you can then do this. But yeah, we didn't think that was a baseline, but I agree, it would be fast. And you wouldn't be able to exploit the correlations between sensors close to each other.
How many inducing points at each slice of time? What's MS? Do you know in this case?
What was MS?
The 60K, I guess, you got from repeating it.
Yes.
Like the number of times.
Yes, I think it was, because there's about 70, from memory, this is a few years ago now. So I think there's 70 static sites, and I believe we chose MS to be between 20 and 50. So it's not tiny, but it's not massive. Don't hold me to that, though. I'd have to double check the exact number. But yeah, most of this 60K is coming from the fact that we have those 20 or 50 inducing points repeated at each time step. Yeah, this is just a table of results just to prove that we did better. Right, there's lots of extensions. I'm just going to say we can do spatial mini-batching. One thing that I have not talked about, which is actually quite important, is that the natural gradient update is not always a valid update. So if you have a non-Gaussian likelihood, you need to start worrying about the positive semi-definiteness of your update. You need to ensure that your update is PSD. And the standard way to do that is to use some kind of Gauss-Newton approximation. You can look at these references by M.T. Khan and Will Wilkinson. And because we have a state space model, it's very easy to include derivative observations, and it's very easy then to kind of start to think about how to do like a physics-informed GP within this framework. Yeah. So just some kind of future work points that just to kind of summarize. Ultimately, the bottleneck will always be the state dimension size with this stuff. So yes, we can use it as spatial inducing points, but what happens if you have loads of spatial points and there's lots of structure that you want to capture? You're suddenly in the same problem where you need lots of spatial inducing points. I don't know the solution to that. If you do, come talk to me. That would be great. But yeah, so that's ultimately going to be the bottleneck of these models. And of course, you can apply this beyond just vanilla GPs or single latent GPs. You can do maybe deep GPs and multi-fidelity GPs and physics-informed GPs. The world's your oyster there. So yeah, I'm going to stop there because we're getting late. And I'm going to say thank you all for listening and for sticking around. Hopefully that was interesting. And yeah.